This is Software Engineering Radio, the podcast for professional developers on the web at se-radio.net. SE Radio is brought to you by the IEEE Computer Society and by IEEE Software Magazine. Online at computer.org/software. Invent your future at CACI, a national security company revolutionizing technology through digital, C4ISR, cyber, space, engineering, and IT transformations. You'll deliver information dominance through the development of next-generation solutions. At CACI, you'll be treated like the company's greatest asset. When a company believes their people are their greatest asset, they let the best do what they do best. Visit careers.caci.com/innovate to explore CACI's engineering and IT opportunities.
Welcome to Software Engineering Radio. I'm your host, Gavin Henry, and today my guest is Tim McNamara. Tim learned to program so he could assist with humanitarian disasters around the world from New Zealand. His area of professional expertise is in natural language processing and machine learning. Tim is also the author of Rust in Action, an introduction to Rust for programmers who have never used a systems programming language before. He currently works at TCDI, an American legal services and cybersecurity company, as a senior software architect. Tim, welcome to Software Engineering Radio. Is there anything I missed in your bio that you'd like to add?
No, it covers it. Thanks very much, Kevin.
So the goals for today's episode on a Rust 2021 edition is to revisit why and when Rust was created, because we did a show, episode 279, with Florian Gilcher, I think, on Rust back in 2017. So that was 4 years ago. So we're also going to learn to understand when to use Rust, its top 3 benefits, to explore what's changed since our 2017 show, and to understand what an edition is and what the 2021 edition brings. So the first question is, the Rust website headline is, "A language empowering everyone to build reliable and efficient software." What does that mean?
That's an excellent place to start. The Rust programming language is explicitly, or at least the community that surrounds the Rust programming language, is explicitly there to be able to support anyone achieve their goals with software. By the safe and reliable aspect is probably the easiest one to mentally grasp, and that would be to say that all things being equal, your application should use the least amount of memory and the least amount of compute resources in order to achieve its aims. So effectively, Rust is attempting to eliminate waste, and both in terms of compute resources but also human resources. We shouldn't necessarily need to have security vulnerabilities or random crashes. You know, our systems that we build, these software systems, should actually be stable and robust. And that is sort of the technical side of Rust. Now, the empowering everything is kind of this value-laden statement that's intentionally there as a bit of a jibe, I think, at other language communities or other open source communities. It's saying, well, actually, everyone is welcome. And you shouldn't feel that if you've only done JavaScript, or you've only done Python, or you've only programmed in Java, that you are not entitled to learn about low-level, high-performance software. You definitely have a place in the room. We're trying to attract a very wide spectrum of developers so that the whole ecosystem supports a better software industry, a software industry that's robust, a software industry that respects its users, a software industry that respects programmers as a profession.
Well, I think you've touched upon a few of my follow-up questions, so that was good. Can you remind us why and when Rust was created for those that haven't listened to the show in 2017?
Right, so Rust was originally made public by Mozilla. So the organization had this problem. One is an existential crisis, which is Chrome came about, and they tried to rapidly enhance Firefox in response, in particular the performance of its JavaScript engine, although the details are probably somewhere in between. But it turns out that C++ is extremely difficult to actually get working in a very large team. And there were concurrency bugs. There might be this memory management kind of problems about a classic example is called a double free, where you might say that memory has been freed, and then some other part of the program actually goes and tries to free it again, which is illegal behavior. Another case that Rust completely eliminates by design is iterator invalidation. So if you change the array while you iterate through it, let's say you're adding or removing items, this is like a source of really bad bugs. And Rust actually ensures that illegal or, we might say undefined behavior is completely impossible. We have whole classes of bugs which just don't exist in Rust. And therefore, why Rust was created was to create a better C++. It was there to be able to enable very large systems to be built with it. And that involved creating a productive and relatively ergonomic language that people who were not expert developers or would never see themselves as sort of expert systems programmers would still be able to produce reasonable code. And possibly, moreover, they wouldn't be able to accidentally insert massive security vulnerabilities inside a very important piece of software.
Does it do these checks and optimizations? Well, not optimizations, but lets you know about all these things when it's running or before it gets to the point of being, I presume it creates a binary, does it?
Right. So Rust is a compiled language, and therefore the compiler has an opportunity to check before any program is actually run. It turns out that almost all of Rust's safety checks are actually checked at this compile stage. There's actually no runtime cost at all to any of these safety features. What Rust does is kind of tag data with a lifetime. Just imagine we didn't have any conditionals in our program. We only had a very linear way through. And you would know that, let's say, variable A could last from, say, step 10 through to step 50. And then, for whatever reason, after step 50, accessing that variable A was illegal. Rust does a similar kind of analysis across the entire program, across every thread, and it does it all at compile time. There are one or two cases in which you will incur a runtime cost. So, for example, if I try to access the 9th element of an array, or so if I look up an array by index, there will be a sort of what we call a bounds check to say that the 9th element actually exists. It is slightly possible to get around that with higher order programming, and in particular the functional paradigm. And you can mutate or perform transformations on some data structure with closures, which are anonymous functions. And they are typically very heavily optimized by the compiler, and idiomatic Rust will often not require bounds checking at all because it can guarantee that it will only access safe and valid memory.
So there's certain ways to get around that optimization and safety.
There are a couple of different styles of programming. Say an imperative style with for loops and accessing with an I. So you can imagine that you've created your index variable I and you're sort of iterating from 0 through 10. Rust doesn't require you to manually create an iterator, like this index variable. That mode is available to you. And it's sort of this mode of being very imperative. And it works, but it's going against the grain slightly. And the sort of idiomatic Rust approach will typically be faster. It's slightly more memory efficient because it wouldn't require the use of temporary variables.
We've covered why and when Rust was created. Briefly, when should a programmer use Rust?
I don't want to speak for every programmer, but I can talk about when I use Rust. So before Rust, I had basically used Python for about a decade, and that was my programming experience. And I used Rust, or I kind of leaned towards Rust when things were too slow, is when I turned to Rust. But actually, now that I am productive with it, it's a surprisingly versatile tool. I tend to kind of use it for command line utilities and all the way through to kind of network services. It's quite heavily used on the back end of the web site. So for developing web APIs is quite a common use case, as well as this ability for Rust to compile to the front end via a technology called WebAssembly. Rust also has a special place to play inside embedded programming. It doesn't require an operating system or an interpreter to run. And so it can actually be compiled to microcontrollers as well. It can fit in a very wide range of areas. And where I found it particularly useful is data processing, like high volume, so terabytes and more of mostly text data. But it does it very, very quickly, and it uses very little memory.
And what sort of companies, people, organizations are using it?
Rust has been adopted by all of the marquee tech companies. The Rust Foundation, I think, is sponsored by at least Microsoft, Google, Facebook, Huawei, the Chinese tech company, Mozilla is heavily involved. The best milestone would be 2015, as when the 1.0 released. There was quite a lot of work prior to that. So I think the first public announcement at all was around 2008. Or at least that may have been when the original developer, Graydon Hoare, actually started working on it. There was a long period where the language itself was effectively considered unstable, where Rust wanted to be able to, if you think of its original use case, developing an alternative web browser, it was actually being developed in lockstep with this big software project. And they were molding the language to make it more and more productive. So there was a very, very long process of developing language features or ripping them out or inserting them pre-stabilization. The milestone that matters is 2015.
So what it was getting thought about sort of 3 years after Go was coming around, I think 2005, yeah.
When they were both announced, I think Rust may have been publicly announced around 2012. Rust and Go looked very similar. So they both had something that looked very akin to Go routines, also known as coroutines or lightweight threads, and the ability to kind of spawn work was baked into Rust, but that was actually pulled out of the language as it stabilized, and it became a language that became much more aligned to its peer languages, predominantly C++, and it took on a mantra of zero-cost abstractions. That is, that any given abstraction should have little to no runtime cost at all, and preferably no memory even. So there are quite a few things that are available to you, or they look like types inside the Rust source code that the compiler will actually completely remove inside the binary. They purely exist as the ability for you to mold your program as you'd like it, but they don't actually impose any runtime cost, and they don't have any runtime memory.
Who is using it? I was doing some GitHub Action workflow exploring last week and noticed all of their containers that you can use in GitHub Actions have Rust pre-installed. So I thought that was a very good sign, but obviously GitHub is owned by Microsoft, so that probably explains some of that. So does Rust have a package manager?
Rust has an excellent package manager. Cargo is its name, and Cargo is one of the most fantastic pieces of software that I've ever used. And I say that as someone who was always terrified whenever I was told that I needed to compile a native extension for some Python package, because you would need a C compiler, and then you would always encounter kind of weird linker issues, and I had no idea what I was doing. Rust almost completely eliminates that whole problem, and Cargo just works. It's ridiculous how good it is. It's almost worth using Rust just for Cargo because it avoids you so many problems.
That's some statement, isn't it?
It's surprisingly valid. I mean, coming from Python where there's like 16 different ways, I exaggerate, but of the setup tools, there's distro tools, there's a whole bunch of other new ones. Is it poetry? Is it pip? Is it, if you're in scientific programming, is it conda? And then all of that is eliminated in Rust. And it feels fresh. I don't want to evangelize too much, but also just I keep looking for the disillusionment with Rust. Every single tech thing that I get excited about, after 9 months, say, something will just hit me and it'll just be terrible, and I'll look for the next thing. But with Rust just keeps getting better and better and better. And yeah, I'm just rapt at the ability to be part of that story.
Well, that's really good to hear. So now that we've had a good introduction to Rust, let's start exploring some of the top 3 benefits. On the Rust website, it says that Rust has performance. So let's talk about that in this section. How do we measure blazingly fast, which is one of the claims?
That is one of the claims. So the claim is that Rust will run blazingly fast. And that statement is kind of paired up with the notion of called a garbage collector. And a garbage collector is a piece of software that runs alongside your application if you're running a Java app or anything on the CLR. So if you're in the .NET ecosystem, or if you are a Python programmer or a JavaScript programmer or a Go programmer, you'll have a little utility that's kind of bolted onto your application that's managing memory and requests for memory from the operating system on your behalf. It takes time to run, and in some cases, in fact, many cases, it will actually halt the execution of your program so that it could do its own work, and then very quickly swap. It'll turn itself off and give your program access to the CPU. Rust does not need a garbage collector. Every single allocation of memory is actually defined at compile time. But unlike, say, C or C++, you never have to manually request it. The compiler understands exactly when every single element of memory is required. It will only access exactly what is being run.
We touched initially in the introduction about most things being done at compile time, where all the safety checks and memory and tracking and looking at how things are going to go. So let's just take an example where we've got a data structure that comes in over the network, but we don't know what's going to be in it, the size-wise. How do you deal with the memory and efficiency and predictable performance when you've got unknowns from users? How does Rust do that bit?
Rust will give you a couple of options. It provides you with the ability to say manually that I only want, say, 4 megabytes of RAM available to this incoming string or this incoming stream of bytes. It provides you with the ability perhaps to say that you can just process them on the fly as they come in. Otherwise, it also gives you kind of tools to be able to say that you can use as much memory as needed. And so the language itself is going to try to provide you with the tools for you to kind of make the decision as the programmer. It's going to try to not impose its own will on you in terms of that particular use case. Does that make any sense?
Yeah, I think so. The way Rust has been explained to make the best choices for all this stuff so you don't have to worry about memory management and wait for the garbage collector. And they're always getting better every year. But it sounds as if you do know what you're doing, you can help Rust make its decision. So that makes sense.
Right. I think it does. Let's say that I wanted to accept an HTTP post request. So someone is submitting a form, and we don't know how long the form is, but we want to guard the server that is hosting the application from being overrun with data. The thing that's most likely to happen is that you will read in only the amount that is required. So it might be one form element, and then that will be processed. The web framework itself will probably have a guard in there, which says that once I've hit, say, 2 megabytes or whichever limit that you've provided, that actually the client will be cut off. The framework will return like the too large response. In terms of, say, TCP or sort of raw TCP, the similar thing might happen.
Try to understand if there's no runtime and no garbage collection in the build process, the compilation, how does it know, to handle a variable memory requirement? That's what I'm trying to drill down to. I'm thinking like the compilation style is like the stages. like running scenarios and predictions, but it's not, is it? It's looking at all the different flows through the program, or?
That's right, yes. So one of the things that kind of hits you in the face when you try to learn Rust is that suddenly you read something and jargon starts getting thrown at you. Some of the jargon that we talk about is the stack and the heap. Now, the stack and the heap are actually not data structures in the classical sense. You never see them in your program. But the way that a systems programming language like Rust deals with an unknown number of bytes is through a process called dynamic memory allocation. Rust will request more memory from the operating system as it's required. That's why it's called dynamic. But there's a problem, and that is it doesn't know where to put it at compile time. So instead, Rust will allocate the size of a pointer, which is a memory address. So it's just a number, just another integer. And that integer, along with a length, which is another number, so those are two things of fixed size, will point to some other area of memory that will be allocated by the operating system at runtime. We encounter a couple of bits and pieces of jargon, and one of them is unfortunately named term of like a unsized type. In Rust, an unsized type is a type that doesn't have a sort of a complete known length. Let's say like a string. We don't actually know how a string from some unknown source. We don't know how long it will be, but some parts of it are known. And normally the parts that are will be a pointer, a length, and in the case of a string, we also retain the capacity, which is how many bytes we've actually allocated, with sort of there's a backing array as well that we point to. Now, the cool thing I think about Rust is that you don't actually need to know about pointers in order to make use of the language. As your skills increase, you can kind of dig in and learn about them. It's not forced upon you. That's, I think, one of the reasons why the Rust community has kind of chosen to say, we are here to empower everyone.
It sounds like most of the effort is done at compile time to figure out what you've told Rust that you might need, but it also will figure out what it needs. So does that mean build time takes longer than it would with another language?
Rust compile times are relatively slower, so it's in some of its peer languages. The Rust compiler is doing more work. It is tracking the use of all of these variables. It turns out also that with some of the implementation details about how the compilation steps work mean that Rust's compilation model is slower, but not for the reasons around dynamic, not for the memory allocation thing.
When we talk about blazingly fast, that obviously means runtime, because we've talked about the build time. Where would you see blazingly fast sit in, with the rest of the language ecosystem? If Rust is pitched as a C++ replacement and Go is pitched as a C replacement, does Rust fit in somewhere between the performance stats of C and C++, or how do we put some numbers against blazingly fast? That's what I'm trying to get to.
Yeah, sure. And that's a perfectly valid question. The Rust community has put this outrageous claim out, so it's time for some evidence. So I'm going to make another possibly outrageous claim, and that would be that I would find it easier to write faster code in Rust than, say, C or C++. And that is because a lot of the abstractions are really ergonomic and are very difficult to misuse. Whereas I think I'd be anxious about my own capability if I were to try and re-implement something in a language where I would have much more manual control. Rust provides you with the equal level of manual control if you need it, but it's there for you, so it's still available. Whereas C and C++, in many instances, it's required that you actually do that. So where does Rust sit? I'm thinking of two main benchmarks. There is a site that used to at least be maintained by the Debian project called the Benchmarks Game. Now, this is a sort of a series of benchmarks which consistently demonstrates that Rust is on par with the highest level of performance available. So Rust is as fast as the fastest languages. One of the reasons why it's named Rust is that you can't get closer to the metal. At least that's one of the slogans. The other thing in terms of benchmarks, there is a web benchmark. One of the Rust frameworks is able to serve, I think, concurrently 7 million requests per unit. And I can't remember if the unit is second or minute. I believe it's actually second, which strikes me as a ridiculous number of requests.
Yeah, I need a big pot of bandwidth to serve that.
Yeah, you start saturating the neck there at that point. So Rust is consistently good. One of the other, this is much more anecdotal than those kind of two benchmark sites, but someone who I respect a lot, his name's Brian Cantrell. He has recently started with a couple of co-founders, the Oxide Computer Company, and became notable as the creator of the dtrace project for Solaris. And he has quite a fascinating blog post where he says that, I've been a C programmer for decades, but my Rust is faster. And that's because it's just much easier to write fast code in Rust.
That makes sense. Okay, so one of the top things Rust lists as a major win is reliability. So let's take some time to explore that. What is a rich type system?
A rich type system is a type system that enables you to express your intent really well.
That helps with reliability because it can optimize for that specific type and make it more predictable, or?
So Rust does not have exceptions. Its place has this notion of a result type. A result is sort of a placeholder value that can either be a successful return value or an error case. So we call this the OK or error. Now, if I return a result from my function signature, so if I declared my function as having result, then every caller that uses my function must take account of the fact that it could fail. It's impossible to compile a Rust program that hasn't included checking of error cases. It's simply not possible to kind of skip over an error code.
That would apply to memory safety, thread safety, concurrency, anything.
Absolutely. The other type that I find particularly cunning, really, is the option. So Rust encodes missing values with this type that we'll call option. And I think Haskell calls it optional. So Rust value could be present. We say there's some value, or it could be missing, in which we say there's none there. Now, this looks like each of those two cases look as though they would take up memory. But it turns out that the none case is completely invisible in the final binary. It uses some really neat compile magic to kind of prove to itself that it actually never needs to represent none in the actual binary itself, because of the fact that if something is present, then it will never be null. It turns out that this is a genuine zero-cost abstraction. We have complete type safety from the point of view that if something takes an argument at option, it's impossible to work with that function and not take account of the possibility that a value may not be present.
So does that touch on the ownership model guarantee?
Similar but different. Again, so ownership is another concept that gives you some of this reliability and robustness, but it works in a slightly different way. The optional case, though, is really just there to say that it's impossible to treat a function and sort of silently hope that a value will be present. Like a none or some sort of nil value or null, depending on your preference, sort of turns up, you're not going to suddenly crash. Or if I carry on with some kind of erroneous value. You raise a very good point, though. There's this kind of notion of an ownership or an owner that we haven't really discussed in this conversation.
If ownership is tracked, then you know who owns that bit of memory and you know who owns that bit of data that gets shared between threads or things like that.
Absolutely. The first thing to say about ownership, I think it's poorly named. So ownership in a Western mindset implies that you are able to prevent trespassers from accessing things that you own. That is what ownership means. It's sort of the ability to exclude others from access. And it turns out that in Rust, the owner does not have the ability to restrict other parts of the program. Like, no one comes and checks for permission for the owner. It's impossible for the owner to ever decline a request for accessing the data that is owned. The owner only has one responsibility in Rust, and that is to free or to delete the value that is owned at the end of its scope. So if I own some integer at the end of my lifetime, I need to make sure that integer has already been deleted from memory. Turns out that this is all implemented with scopes, and there's actually no requirement for you as a programmer to kind of call delete. It just happens to be the case that when my lifetime ends, that everything that I own is also deleted.
Invent your future at CACI, a national security company revolutionizing technology through digital, C4 ISR, cyber, space, engineering, and IT transformations. You'll deliver information dominance through the development of next-generation solutions. At CACI, you'll be treated like the company's greatest asset. When a company believes their people are their greatest asset, they let the best do what they do best. Visit careers.caci.com/innovate to explore CACI's engineering and IT opportunities.
We touched a little bit of this on the introduction, and something I want to ask just now is about the safety and ownership you've mentioned there and the build time length. I'm just doing some C work at the moment, and I think part of what you've described in the build process where it looks at the safety, if you were to take C and what we've just spoken about scope, I'm doing something where it opens a socket, a UDP socket, and then depending on whether that's successful or not, and some other bits of memory, you return from the function and the variables you've opened behind the scenes of that variable, some memory's opened, go out of scope. So it's my job as a C programmer to understand that that file descriptor takes some stuff and leaves it open, and I've got to shut that down. Now, if I hadn't have thought about that, which I didn't, I've got this program plugged into some static analysis tools like CodeQL on GitHub, Clang Analyzer, and the Coverity one that checks for loads of different things in C. And it was only the Coverity tool that picked that up and said, look here on line 57, you've opened up some stuff, you've checked the return code, but the variable's gone out of scope and you're leaking memory. So how I understood what you've described just a minute ago in the introduction is all of those third-party things are all scooped together and done at build time with Rust.
You are correct. So in terms of just Rust, in terms of like opening and closing sockets or some resources, Rust will kind of wind things down, but it's actually dependent on the library itself that, you might have some UDP library that knows about sockets. One thing that Rust doesn't guarantee is that your program will be free of memory leaks. So it is potentially perfectly memory safe to just leak memory. If you know that nothing will ever access that region, then Rust will still compile it if you were to kind of go under its back and kind of re-implement some of the functionality that's provided in the standard library, for example, and you wanted to be able to rely on the fact that you're writing a short-lived utility, then you expect that the operating system will just clear everything up when you're done because it's only going to be alive for 10 seconds, then you can leak memory deliberately, and there isn't a check there.
Memory safety is more about accessing memory that isn't yours.
Exactly. Rust will get very, very particular, very stroppy with you in as polite way as possible. If you attempt to access, actually I'll be a little bit more precise what I mean by access. Multiple readers is fine, but there can only ever be one place in your program that has write access to any given value, and Rust implements that without actually any locking. So it can guarantee, in the most part, that exactly when it is safe to access values and to modify them without needing to add extra locking mechanisms. Now, if you do wish to have a shared variable that is writers in multiple threads, for example, you will actually be required to place some form of locking or some sort of synchronization mechanism in front of that variable. But in the single-threaded case, if we had multiple references to some object, only one of them could ever have write access.
Does it figure that all out at build time? Basically, once you've got that binary, you know you're good.
Once you have your binary, you're good. But wait for the but. Wait for the... Rust provides the ability for you to call what we call unsafe functions with an explicit unsafe block that is clearly very, very visible inside your source code. This is very common, this kind of pattern of, we talked about C just before. If I want to import or sort of link in a library that provides some useful functionality, say some compression library, and it requires a pointer and a length to the bytes that it wants to compress, Rust isn't able to provide any guarantees at all about what the C library does. It doesn't have any way to kind of introspect that library's functionality. And so there are some sort of escape hatches to be able to create raw pointers to do things that are dangerous. You can cause crashes in unsafe Rust, but you need to opt into that.
That makes sense. There's an article I found on the IEEE Computer Society website, which is obviously what runs this podcast, called Securing Unsafe Rust Programs with X-Rust. And they quote here, Rust is a promising systems programming language that embraces both high-level memory safety and low-level resource manipulation. However, the dark side of Rust, unsafe Rust, leaves a large security hole as it bypasses the Rust type system in order to support low-level operations. Recently, several real-world memory corruption vulnerabilities have been discovered in Rust shared libraries. So I guess that's just where people have flicked that switch to use the unsafe Rust and maybe not done it right.
Yeah, it's exceptionally difficult to do correctly.
If you give someone a gun with bullets, well, not. You know what I mean?
Yeah, right. Well, gun with bullets. Here's a loaded rifle. Please treat it with respect. The other side of Rust for me, just as someone who has written a book for people who have never done systems programming before, is that I often use the unsafe keyword examples with inside that book because I want to demonstrate how things are built. And it's quite fun, actually, to say, oh, look, here's a stream of bytes, and they are all, one after the other. But actually, I want to now treat them as an array of integers. And so we need to actually take a series of 4-byte, we want to read in 4 bytes at a time and just treat that in memory as an integer. And actually, that's not magical. Your CPU does that all the time. And I really appreciate that Rust has these escape hatches available for people who do wish to kind of explore. And I've personally been really impressed with this idea that Rust actually kind of supports people's intellectual curiosity.
So when you're ready to do that and flick that switch, you can look behind the curtain and see what's going on.
That's right. You can also annotate your code with these kind of forbid annotations to say that I forbid the use of unsafe in this code base. You can actually decorate your source code with these annotations, which actually we call attributes. Some of these attributes will refuse to compile your code unless it complies with certain style guidelines, which is actually surprisingly useful with things relating to, say, memory safety.
So productivity for the developer or for the team, what's the documentation like?
Pretty good. And on the whole, I think there are areas that are spotty. So that's particularly in the sort of the third-party ecosystem. But I think in the standard library, the documentation is excellent. The language itself is well documented. There is a free online book that you can download that's available to you that details the entire language.
It's not as good as your book, though, is it?
Well, books are different, right? So mine is intentionally different than other material. Mine is about examples and saying, okay, so you want to know, let's implement a CPU emulator. Let's implement a database. Let's implement an NTP client because I want to understand what NTP is and timekeeping is. And so my book is really around giving you enough foundations of Rust so that you can actually manipulate that and extend it. Whereas the free book is called the Rust programming language, is really just, we'll start at integers and we'll walk our way through all the way through the language and all of its language features. And then at the end, we will get to an example.
What's a friendly compiler?
A friendly compiler is one that provides you with specific errors that point you at the right place. It gives you a concrete reason why something has broken, and it gives you suggestions for fixing it. And most of the time, the suggestions are very, very good. So Rust is a friendly compiler in the sense that every single error message includes a link to a web page that has a very detailed explanation for what this error is and why it is caused and how to get out of it. For me, as someone who had never really used a compiled language before Rust, I am heavily indebted to the compiler team itself.
Is the compiler the same thing as a build tool? Is that all in one?
Good point. There's a small ecosystem of tools. It's a trio of tools that comprise kind of the standard toolchain. Sorry to throw more jargon into the conversation. So we have the Rust compiler. So this is known as Rust C. It is responsible for taking your source code and taking the source code of all of your dependencies and massaging them into an executable binary or a library. Alongside that are two pieces of software. One of them we've talked about called Cargo. Cargo is responsible for downloading those dependencies, kind of rearranging everything so that it's easy for Rust C to know where everything is. And it also actually invokes Rust C itself. So your day-to-day Rust programmer will typically run Cargo build rather than interacting with Rust C directly. The third member of this trio is a tool called Rust Up. And Rust Up is a tool that manages toolchains. And you might say, well, what's a toolchain? And the toolchain would be whether or not, for example, you're running the stable Rust compiler, or you might actually opt in to the nightly compiler, which has kind of got more features, but actually comes with the possibility of stability problems because things aren't quite finished yet. It also provides you with the ability to install a Rust compiler for other compile targets. So you might be running on Windows, but you want to compile for Linux, or say you've got Rust on your MacBook, but you actually want to compile for some other target or your little microcontroller, and Rust Up manages all of that.
Oh, excellent. So we did a show on Rust, like I said, in 2017. Is there a quick way to say what's changed since then?
Since your chat with Florian, there have been 2 Rust editions. A Rust edition is an opportunity for backwards incompatible changes to be included to Rust, notwithstanding that if you opt into a new edition, your old code will actually still continue to compile. And so Rust's actually a very stable language. There were several changes made in 2018.
So would it just be a case of looking up what changed and applying that to your code?
That's right. The thing to search for would be Rust 2018 edition. In fact, there is an edition guide as part of the official documentation. And the 2018 changes were created out of playing with the language in anger for a couple of years as an open source or major open source project. And it simplified a lot of things, which actually added to the ergonomics. The 2021 edition kind of just adds even just a tad extra polish. It provides just a couple of niceties. For example, the ability for you to have a conversion operation that may fail. So instead of it crashing on you, it returns a result, which we actually talked about a few minutes ago. And just a couple of syntactic niceties that aren't available to previous editions of Rust.
And what do you have to change to use a newer version of Rust? Is it the toolchain or Rust C? Or
to opt into the new version of Rust, every Rust project managed by Cargo has a little metadata file. All you need is edition equals 2018. It's sort of like a little ini file or a little config file.
If you're using quite a lot of libraries from crates.io, would it just be a case of doing the usual thing where if one of those doesn't work under 2021? You open a ticket in that project and get up to speed, or should it always work?
You can still include third-party dependencies that themselves are using an older edition. So you shouldn't actually need to update any dependencies to your compiler version. Today's compiler can still compile code that was in the original 2015 edition. So, but if you want to contribute, yes, raise a ticket, and there shouldn't be anything that could compile that can't. The changes are mostly additive rather than contradictory.
How are these changes proposed and discussed?
So the Rust community is quite special in the fact that it has a very participatory RFC, or kind of request for comments process, where a change might be suggested in a discussion forum, which is then iterated, say, oh, that sounds like a sensible, people have a chat and people might have a discussion and decide that it's worth investigating. That will then be written up as a proposal. And then there are a couple of teams, and depending on which team sort of sponsors the idea, then things can kind of move on from there. As well as additions, Rust has a 6-weekly update cycle in terms of its minor version updates. And so if something is not backwards incompatible, or you're not trying to create something that an old compiler won't understand, then quite often you can include substantive changes inside one of those 6-week cycles.
And if you were trying to keep up to date with that, would you just keep an eye on the announcements and rebuild your binary? Or when do you do that? Do you just leave it running wherever it is deployed, or do you just build that into your deployment type thing?
No, this I think is actually quite an important misconception to kind of squish if we can. The language does have a minor update every 6 weeks, but the stability is still there. Your code will still continue to compile, and no backwards incompatible changes are made in the newer versions. You kind of get new fancy things. You can opt into that.
Okay. What does the future look like for Rust since the whole Mozilla Foundation creation?
My view is that Rust's future is extremely strong. Rust continues to grow exponentially in terms of its adoption. It's receiving a lot of attention, as we said, with these marquee companies. But actually what I'm really intrigued by, or really hopeful for, is that smaller, kind of maybe lesser known companies might be taking it on for sort of side projects and for kind of exploratory work. And that, to me, is where I think a lot of the growth will be. People are excited that it has been the developers' most loved programming language for the last 6 years in a row. But if you can't actually work with it day to day, then it doesn't mean a lot. And what I'm hopeful for is that the ecosystem will continue to really encourage creativity and really encourage people who are willing or interested in learning.
Excellent, thank you. Obviously, Rust is a very powerful language with a strong ecosystem. But if there was one thing that a software engineer should remember from our show, what would you like that to be?
The one thing that I would like people listening to take away is that they can learn Rust, that they can share in its advantages. Don't be put off by the fact that you've heard that it's difficult to learn. There are more resources. There are different resources available. You don't need to follow the same path as everyone else.
Excellent.
Invent your future at CACI, a national security company revolutionizing technology through digital, C4 ISR, cyber, space, engineering, and IT transformations. You'll deliver information dominance through the development of next-generation solutions. At CACI, you'll be treated like the company's greatest asset. When a company believes their people are their greatest asset, they let the best do what they do best. Visit careers.caci.com/innovate to explore CACI's engineering and IT opportunities.
So, Tim, one thing I didn't ask in the follow-up question was, how does Rust run without an operating system? You mentioned that in the introduction.
This is called running code on bare metal, and it involves compiling your binary to something that can be kind of triggered with the BIOS. And this is something that's actually supported by Rust sort of out of the box.
So where can people find out more?
If you'd like to learn more about Rust, I think a good place is rust-lang.org. Me, I'm Tim Clicks, is what I normally go by. So that's TIMCLICKS.
Perfect. And I've got a link for the Rust 2021 edition and the benchmarks you gave me. Thank you very much.
Hey, that's my pleasure. It's
been a real pleasure. This is Gavin Henry for Software Engineering Radio. Thank you for listening.
Thanks for listening to SE Radio, an educational program brought to you by IEEE Software Magazine. For more about the podcast, including other episodes, visit our website at se-radio.net. To provide feedback, you can comment on each episode on the website or reach us on LinkedIn, Facebook, Twitter, or through our Slack channel at seradio.slack.com. You can also email us at team@se-radio.net. This and all other episodes of SE Radio is licensed under Creative Commons License 2.5. Thanks for listening.